Hello there, this is Nev from Star Waders, your very amateur astronomer, and I'm the guy who always asks why. Why do we see things where we actually do see them? So today what we're going to look at is Comet Leonard. Comet Leonard is on its way into the center of the solar system at the moment, and it's visible in the northern hemisphere at the moment, and it's heading down towards the southern hemisphere where it's going to hopefully put on a good show. So what I want to show you is why you see it where you do see it. I want you to understand where it's come from and where it is heading for. So let's have a look and understand what a comet orbit is like, and then we'll see how a comet orbit moves in the solar system, and then we'll have a look specifically at Comet Leonard's orbit. Right, so comet orbits are ellipses. In fact, every object that orbits the sun and in an ellipse. The Earth is in an ellipse, so that means at some stage it is closer to the sun than another stage. It happens to be closest to the sun on about the 3rd or the 4th of January, I think. And but the difference between its closest and its furthest away from the sun is not very much. So it is not the cause of our seasons. So let's have a look at this ellipse over here. This could be any comet ellipse. It's got a long axis and it's got a short axis. If the short axis were the same length as the long axis, then this would be a circle. And the shape of an ellipse is determined by the ratio between the long axis, called the major axis, and the shorter axis, called the minor axis. And an ellipse has two focus points. It's got one and another one over there, second one. And in the solar system, the sun is always at the one focus point. So these are called foci, with the sun at the one. So your comet would move further out, way out from the sun, and then come back towards the sun, go around the sun, and go out again. We are looking at this model. It's part of the solar system, and in the solar system, all planets are considered to go around the sun in an anti-clockwise direction, and so the same is with this comet. That is its formal direction, except you're going to see there's a bit of an anomaly when we get closer to this one later. So this is what a comet orbit looks like. What we're going to do is now go and see how a comet can approach the sun, the different directions from which it can come. In order for me to show you how a comet moves around the sun, I have to allow in the model for the comet to move from the northern side of the solar system to the southern side of the solar system. It has to move through what's called the equatorial plane. So in this case over here, we would have this model here, and it would need to go through and dip through the plane of the solar system, through the equatorial plane. So to make it a little bit easier, I've got this cut-off version of a comet orbit. So our comet would be coming in like that and heading on its way out in its anti-clockwise direction. So what it does, it will go around the sun. So here I'm demonstrating how it goes around the sun, but note how it is gone through the plane of the solar system, and then it comes out again on the other side. So what I want to show you is now all the different directions from which a comet can arrive. So it could come in pretty well in the same plane as the planets are in the solar system. So if the planets are going around like this, it could come in its far more elliptical orbit than what the planets have and move out again. What it could also do is it could come from right up above the solar system and then dip down way below the sun and then come up again. Of course, it could be rotated at this angle. right? Any one of these orientations it could be at. It could be at any one of these inclinations from 90 degrees up here down to 0 degrees. And then the other thing that, other direction, or the other parameter, it could be coming in from anywhere around the solar system. Okay, from this side, from this side. So there are all these various ways that a comet can enter the solar system. Well, not enter the solar system, but these are the ways that a comet can complete its elliptical orbit around the sun. This model is intended to demonstrate on a very generic solar system plane. So what we could consider is we could consider that that's Neptune and that's perhaps Mars, or we could consider that that's Earth and we could consider that's Venus. But in this case, I want to consider that Earth is somewhere very close to the sun here. So you can see that the comet orbit could bring it in fairly close to Earth if Earth was in around about an orbit around this size over here. So we're going to see how we can see the comet from our earthly vantage point. Right now what we want to do is describe the shape and orientation of the ellipse. And this is how we are going to learn how that is defined. So we have these major and minor axes, and it's their ratio that determines the shape of the ellipse. And it is the ratio of the minor axis to the major axis, and that number is called the eccentricity. It is one of the numbers that is specified in determining what the shape is of an ellipse. Now the point at which the orbit comes closest to the sun is called the perihelion. That is down there. And the opposite end of the orbit is called the aphelion. Now what you would have noticed when we were working in the water model is that the ellipse does dip through the water, and it dips through at one point and it comes back out at the other. Part of the orbit is below the plane of the solar system, or the equatorial plane. So these 2 points where it goes through the equatorial plane are called nodes. And note that these nodes, the line between the nodes, always goes right through the sun. And bear in mind as well that the orbit, as with all planets in the solar system, is defined to be anti-clockwise. So the sun will go up past the aphelion, back down again through the descending node, and then up again through the ascending node. Now the comet's orientation is defined by a number of different numbers. So first of all, we have the direction in which the comet comes from in the solar system. And the next one is its inclination to the solar system. So it could be anywhere from flat in the solar system to coming down at 90 degrees. And then we have this other direction, or this other orientation called the tilt. So we could have it, say, in this vertical position, but if we tilt it, notice there that we have the solar system cutting through the sun and going between the two nodes. So that is due to the tilt. And of course, the reason that this is called the ascending node is because we are going from below the solar system, which is the southern side as it's been defined, and it is going up into the northern half of the solar system. And then this here, because that's the direction of it going up, that is called the ascending node. And this one over here is called the descending node because it's going down below into the southern half of the solar system. So the comet's orientation is described in terms of the direction in which it is coming from, and then by its inclination, and then by this tilt, which affects the line of the nodes. So these values are all part of what's called the orbital elements, and orbital elements are available for any object that is traveling around the solar system. And they can be used to be put into astronomy programs, which can then determine the direction and its orientation. Now, to get a better idea of how the Earth's position relates to Comet Leonard, we need a model that is dedicated to Comet Leonard. So we have this model. And there you can see the orbit, and you can see how that orbit is cutting through the solar system. So in this one here, it is coming down on this side. Now I'm going to explain to you why this looks as though it is clockwise, and when I've said to you these things are always anti-clockwise, but we get to that explanation. And it is coming down through the solar system and out through the other side. This here would be the northern side of the solar system, and that would be the southern side of the solar system. So the directions around the sun are given in what are called hours. They can, however, more conveniently be expressed in degrees. These numbers indicate the position of a planet in its orbit around the sun, and they are analogous to the lines of longitude that we have here around Earth. By the way, the choice of where zero is, the zero direction is the subject for another day, and it's a reasonably complicated subject. Now, the directions to the stars and to the constellations are also indicated by these numbers, these hours or these degrees. So it can be seen, for instance, that Virgo is in the direction of 12 or 180 degrees. So we have the sun over there, and Virgo is in the direction of 12 hours or perhaps 180 degrees from zero. Now, while the Earth orbits the sun, the constellations that we can see from Earth change. We can't see the constellations that are behind the sun. We can see the constellations during the night that are in the dark side. So shown here are the zodiacal constellations, and in astrology your birth sign is determined by which constellation the sun is in when you were born. So for instance, if the Earth is going around here and you look towards the sun would appear to be in this constellation over here. Now, these birth signs were set 1,000 years ago, but have changed but the Earth's wobble has changed the positions that we see them in. So whereas Aquarius was behind the sun in about January to February 2,000 years ago, Aquarius is now behind the sun in February or March for us. So here we are going around the sun. When we see Aquarius behind the sun or the sun in Aquarius, then it is our March or February. Now let's just have a look at the Earth's orientation. So let's go through to the southern part of the solar system. Here would be, say, the Earth somewhere along this orbit, and its south pole would be towards the south. So if we had the Earth over there, there we have its south pole looking up. And that means that from here, from the southern hemisphere, it is easier to see objects that are in the southern side of the solar system. Now, one of the ways that the orientation of the comet's orbit or any other orbit is given is stated by noting in which direction from the sun the comet ascends through the equiplane, through the equatorial plane. So if we are looking at this one here, it is coming down and it's going through the descending node, and then it comes up here through the ascending node. Now, just to make sure that you understand why we are looking at a clockwise orbit over there, this is actually the direction from which we can see the comet. And from here you can see that it is going in its anti-clockwise direction. So here, let's see, in which direction does this ascending node lie? Well, we can see over here it's somewhere between 17 and 18 hours, And this is specified in degrees as 255.88 degrees. So if we have a look at where we start from 0 hours and we go all the way around, we can go to 180 and then a whole lot more, and that brings us to 255. So that is one of the specifications in the orbital elements. It has a name, this specific element, and it is called the longitude of the ascending node. What I want to mention about the longitude of the ascending node is you can see that that ascending node is in the direction where Sagittarius and Scorpius are. Now I can show this on a star chart. And here we are having a look at where the comet is shortly about to move up through the plane of the solar system. So if I go forward by 1 day, there it has moved up through the plane of the solar system. And we've mentioned over here that that is in the direction somewhere between Sagittarius and Scorpius. So here we have a look at the southern side of the solar system, and there we have Scorpius, and there we have Sagittarius. So it is somewhere around there that the comet is dropping down into the southern half of the solar system. Another element which defines the comet's orientation is its inclination. So here it appears to us that this is the inclination here. But in fact, the inclination of this, and this brings us back to the direction in which we apparently see the comet moving, the inclination is specified as 132 degrees. Now that is 90 plus another 40 or so. And the effect of that is to turn the orbit upside down in a way. And if you look at it from the other side, that is why its orbit is seen as going clockwise and not anti-clockwise. So then the next thing we want to know is how much does this orbit tilt? So right, it's not coming in like this, it's coming in at this angle. It does have this tilt. And that means that the line between the two nodes does not run at right angles to the major axis. So how much does it tilt? Well, if we go back to this little model over here, the tilt is specified by the angle from the ascending node all the way around to the major axis where the perihelion is. So it can be seen in this particular example over here, where you've got 180 degrees there and plus about another 45 over there, and that gives us 225 degrees. And that is what is called the argument of perihelion. I don't know what is so much to be contested about to make it an argument, but I guess that's a mathematical term. So this angle all the way around here is 225 degrees for Comet Leonard, and we can see it over here. And that angle is given from the side of the comet in which the orbit is anti-clockwise. So over here we are looking at going all the way from the line of the ascending node and all the way around until we get to perihelion, which actually goes all the way through to there. So it's that angle all the way around through to there. So that is called the argument of perihelion. Now we need to know where the position of the comet is in its orbit in time. And the way we define that is by stating at what date and time and minute and second the comet passes through perihelion. Okay, by now we know quite a little bit about this comet, but we don't really know how big it is in terms of kilometers, miles, astronomical units, what have you. We don't know what its dimensions are. So we don't know how far away from the sun it goes to get to its point of aphelion. It's so far away that it's something that we can't really see, somewhere maybe in the Oort cloud. So we need to know one of the dimensions. If we knew the length here of this major axis, that would give us some measure, which together with, say, the eccentricity which is the relation between the proportion between the minor axis and the major axis, well, then we could actually work out what that is, and we can infer from that distances from there to there or from there to there. And then, of course, that means from the sun to the point of perihelion. But now, seeing the comet and actually seeing it at its aphelion and its perihelion is not really the right kind of way to, or an efficient way to get an idea of the size of the comet. And that is done by using the laws, Kepler's laws. Johannes Kepler worked out all the formulas, and with his 3 laws of planetary motion, of how objects do orbit around the sun. So those figures are used initially when a comet is first seen, and if you see it on a few occasions, then from those changes in position that we see, people like Johannes Kepler would be able to then go and calculate what its orbit is. So once they have calculated what the orbit is, then out come these various parameters. But now what we want to do is to be able to put these parameters into a program, and from that program be able to draw the orbit, to calculate where it is at any particular time in its orbit, and then also to be able to forecast where a real comet that we are seeing up in the sky will be seen. So any one of these dimensions here would help us to calculate the size of the comet, but the one that is most useful to us is this one over here, from the one focus point, which is the sun, and its distance to the perihelion. And that is a useful distance for us to know, because it gives us an idea of how bright the comet might get as it goes closest past the sun, and as the heat from the sun melts the gases that are from which it is made, and then releases the various materials and the dust and so on that's in it, and which cause its tail. So the most frequently used distance in that case, and one of the orbital elements, is called the perihelion distance, and it is known by the letter Q. So it is these 6 parameters or orbital elements which help us to define the orientation and the shape and the size of the orbit, and also tell us at when it's going to be performing its orbit around the sun, and when it's going to be at perihelion, when it's going to be in its descending node, and when it's going to be in its ascending node. So what I want to consider now is how do we on Earth see the comet? All right, we know here from the northern side of the solar system that we are perhaps in an orbit around here, and in fact it's going the other way around, it's going anti-clockwise, but we are rather interested in what's happening on this side of its orbit, on the southern side of the orbit. And this is where all the action is really going to take place. This is where it might brighten, even though it's going further and further away from us on Earth. So we might be, for instance, over there. And this is roughly where we are going to be in our orbit around the sun when Comet Leonard pops through to the southern side of the solar system. So you can see that we are actually fairly close to it over there. Now, in which direction are we looking in order to be able to see it? Well, from Earth, we are looking in this direction here. All right? You can see from Earth through the ascending node, and we dealt with this a little bit earlier where we showed that we are looking in the direction of Scorpius or Sagittarius in that area. Now what happens is the Earth is going to move ahead, and this was round about the 12th of December, and it can move ahead to the 3rd of January, and the 3rd of January is when the comet will be at perihelion. So now the comet has shifted a little bit further around in the anti-clockwise direction from where we see it, and over here we've moved around clockwise. So now if we are wanting to look towards the comet when it is in perihelion, we can see here this is our line of sight, and our line of sight is taking us through to Aquarius. We'll see Aquarius in the same direction as what the comet is. Do remember, though, that we will be looking a little bit southwards as well. So we will be looking a little bit, in other words, a little bit south of Aquarius. So let's go back to the star chart and have a look and see how the comet moves in order to get to its perihelion. So I'm going to move ahead a day at a time, and then we can see the comet. There it goes, and it is moving further and further into the southern side of the solar system and moving away from Sagittarius. Here we're on the 21st, and I'm going to speed up, and we're going 26, 27, 28, 29, 30, and this is the 1st of January, and here is the 3rd of January. So here is the comet on the 3rd of January, and what we can have a look at then is more or less in what direction it is. So if we have a look here, we can see there is Capricorn and there is Aquarius. So the comet is somewhere between Capricorn and Aquarius. So let's just show that again over here. If we have a look from where we are, our line of sight takes us through somewhere towards Capricorn and Aquarius. The next point that I want to show you is we can just speak about the ascending node. And of course, this is the ascending node where we're going back from the southern part of the solar system to the northern part of the solar system. And you can see that that is fairly way out in the solar system. It spends a bit of time down here in the southern side of the solar system. And this here is the point where it's going back into the northern hemisphere. Its ascending node is somewhere between the orbit of Jupiter and Saturn. So it takes a while for that to happen. So that is going to take us all the way through until somewhere in April 2024. So it's going to take quite a while to get there. Now, the next thing I just want to show you is more or less why we can see it sometimes in the day and sometimes in the morning sky and sometimes in the evening sky. So if we have our little Earth over here, and this is going to be an exaggerated example. If we had our Earth and we say we are round about there, so that means in order for us to see the comet where it is busy coming through into the southern part of the solar system, we would have to be here at the morning side of the Earth's orbit. Let's quickly have a look at this Earth's orbit. Here we are looking towards the sun. As we rotate through and we get to the position where we lose the sun, we can't see the sun any longer, and that is our evening. We go all the way through around in our rotation once a day, and we get here to the point where we can begin to see the sun again shortly before the sun rises. And that means we can actually see here in this one here, we can see the comet in our morning sky. But when we have moved around to around about there, what we are now doing is we can see the comet further in this direction, which means we can see it from our evening sky. There's our evening, and our early evening sky, we can see it there. If we were here in the morning sky, we'd have to look through the Earth, through the body of the Earth in order to see it. So by the time that we get around into a position where we can see it, we have daylight and we can't see it any longer. So that's it. That hopefully gives you some idea of how Comet Leonard is going to come into the solar system and how it's going to interact with Earth. And if you're interested in the orbital elements, this will now give you some idea of how the orbital elements are used. So see you soon.